So hi everyone, good morning. I hope you had a good sleep last night. So we are starting 2 minutes earlier, so I have 17 minutes. And it's really good to have only 15 minutes because this keeps me at point. I shouldn't be boring for any moment. I better use my 15 minutes really good. So Robots Go Mental is a company that's really new. We just started. We have just landed our first big customer, which is Coca-Cola. They're also speaking today at 1:45, I think. Fotios will tell you what they do at Coca-Cola. Maybe he will mention one of the projects that we are involved in, maybe not. I will not speak about that. If he doesn't mention it, probably I'm not allowed to talk about it anyway. So, but I will talk to you about something else. I'll talk to you about something else that we do at Robots Go Mental. I just want to mention that all other customers are startups, and we also consult startups. And it's really interesting business to consult startups because they don't have money, so they tend to pay with some stake in a startup. So I start slowly feeling like I'm an investor, angel investor. Like I feel, what is it like to be an angel investor, even though I'm not an angel investor, because you get a little stake here, get a little stake here, and you're taking a bet with these people, right? So I was thinking this morning, maybe I could call myself AI solution angel, right? I don't know if that could be like a profession. I don't know, but I'm like, people get me into it somehow without me planning to do that, right? What I want to talk to you is about new machine learning technology that we are developing at Robots Go Mental. And before I tell you about that, I'll tell you briefly about me. So I have like several different phases of my life. So much of my life I've spent as a neuroscientist at the Max Planck Institute, where I use machine learning and AI to understand the brain, so to read the signals from the brain. What Elon Musk is doing right now, I pioneered this type of research in my lab here at Max Planck Institute. Right? On the other hand, I looked at the brain to understand better the brain, to be able to apply the brain tricks into the artificial intelligence. Right? I also started several companies. I worked as a consultant for several companies in AI and data science, and also led some groups, mostly in startups. Now, the new technology that I want to tell you about that we are developing. So, as you know, the standard today is that you build a model and then you put it in production. And the rule how you do it, you do learning, training of the model only while you are building it. You have to do it at a safe place with proper data, with proper testing. You have to have your test data set, validation data set, and so on. Once you're pretty sure it's going to be a good model, then you put it in production. Once it's in production, there is no more learning allowed. Right? It has to be a fixed model. That's how it works today. And that's kind of a problem, because the world changes, right? And our own brain also learns as we go. We don't stop learning when we get out of school, right? We keep learning. You know, I learned yesterday a lot here, right? I'm learning right now. So that's a problem for AI. And why is it a problem? Why is learning not allowed? Because the way how today's deep learning works, it's actually too dangerous. People have tried it, it never ended up well, right? There's a famous case of Google having put their model out to interact with people and learn while interacting in the model, like within a week became racist and all kinds of bad things happen when they were learning without a control. And that's a problem we have solved. That's a problem we have solved. We have found a technology by copying some of the knowledge about how this works in the brain, allowing machine learning models to learn with small amounts of data, to be basically guided in a certain direction where you want it to learn, and to avoid huge space of possible states of the network that are not desired. Right? We have now, for this, we have developed the basic theory, we have wrote a paper, we have developed a library, we have made lots of demos. What we are missing now is use cases. That's like the next challenge that we need to tackle. So I'll tell you more about this. So the basic how it works, you can think about it. Here below is your classical neural network. It could be any type of neural network. To check time, I'm good. So it could be any type of neural network, and on top of this neural network, we have a certain knowledge layer which tells this network which of its own parameters it's allowed to change and which of its own parameters should be kept fixed, which of the parameters should be just changed a little bit, and so on, right? So this part on top is called guiding matrix. And this is something that you first have to learn in a laboratory situation, and then with this matrix you go out into the real world. We wrote a paper about it. You can go read and see the whole algorithm. We also have a library in the GitHub. You can go and use the library. We have done, NASA has discovered it, and they come to us and say, like, we have a problem that maybe this can solve. They had RNA sequences of mice that have spent some time in the space, and the problem was they had a very small amount of data. Right? They had only 6 mice in the space shuttle and 6 mice on the ground. And the classical machine learning models could not deal with such complex problem with such small amounts of data. And of course, extending the data set was prohibitively expensive, right? Because you need to go to space to get more data. So they applied it, and their results were very good, right? I don't know anything about RNA sequencing, but I trust they knew what they were doing. And what they found was that by using our technology, they were basically let me explain this. They developed first a foundational model for RNA using all the mice data for RNA on Earth, then used our technology on top of the foundational model, and then used their mission data from space. And what they found was that you basically cannot overfit anymore this model, which is guided by this type of metrics, right? And we published a paper together, so you can look it up as well, right? We also have a patent pending. We got a small grant from Hessen to pay for the cost of patent. We are also doing a project with the AI team, AI students, basically at the Frankfurt School on Finance and Management. So it all looks good from this perspective, and we are kind of doing really great. But identifying use cases is really hard, it's surprisingly hard, right? And I was thinking, like, you know, historically, I mean, we know that we have something really, really good, and still it's hard to find the right use cases. And if you look historically, like when people invented a computer, right? They had this amazing machine, like the first computer, amazing machine that can do so many calculations per second, I don't know, 100 back then. And then it can do logical operations like 100 times faster than a human. Back then, now it's like trillion times faster. But anyway, like you have this computer back in 50s or whatever. They didn't think, they couldn't know immediately all the use cases, right? I'm sure they didn't come up with word processor, right? Or Excel sheet, or email. They were just feeling like, oh, that's gonna be great, but we don't know how, right? I think the same situation is today with large language models. Like, they're great, but we feel they're great, but we are still in a process, as the entire field, of discovering in which ways they are great, right? What is it really great, right? So we are struggling with the same problem. We have some really, really cool technology, and we are struggling to figure out what is a really good use case for that, right? And that's what I need your help, like if you have some ideas. So let me tell you about interesting properties that we have discovered, some hints in which direction it could go. Right? So we have seen that this technology, we have demonstrated that this technology can do pretty good one-shot learning. So we have trained it to learn, for example, to recognize such new letters. And the blue line is when we add the guiding transfer learning, the guiding metrics, and the red line is just the classical machine learning without something, right? So you get great advantage there. Another interesting thing we discovered was that, there are some problems that are really, really hard for machine learning, right? So deep learning cannot learn all types of tasks easily. There are some tasks that are really, really hard. And the really hard ones are so-called logical XOR problems, when you expand them in a huge dimensional space. Right? You have just ones of zeros that map into another bunch of ones of zeros, and behind that you have lots of XOR operations. That's really, really hard for machine learning. And what happens very often, you try to training it, and it's just trying. For thousands and thousands of epochs, it doesn't find a solution. Occasionally it finds a solution, then there is a breakthrough moment, when the deep learning finds a solution, and then very quickly your accuracy goes high up. But it takes really, really time. It's kind of gamble, depending on your initial conditions. So if we could train a guidance matrix for this type of problems, and then start a new random network with a new random super complex XOR problem, and the network would just make these breakthroughs much, much faster. These are the green ones. And the gray ones are without the guidance matrix, right? So that's another advantage. Yet another advantage we discovered was that since you basically do not allow most of the parameters to change, and you allow only some parameters to change, the network does not forget stuff. It can basically accumulate knowledge, right? So one classical problem in today's machine learning is that if you want to add more knowledge to the network, you have to train the network with all the data that you trained it before. Because if you train it only with the new data, it will forget pretty much immediately the old data. It's called catastrophic forgetting, right? So what we found was that we could add new examples of the same category, just one example on top of the previous example, and for a while we could just keep increasing the performance without losing it. There's a limit to it, of course, and here again, comparison. When we switch off the metrics, what happens, right? Okay, now I have another 4 minutes, perfect timing. So I'll tell you, as the last thing, I'll tell you what kind of ideas we are working on for use cases. None of those we have really proven that it works, but we are working on it, right? So one is in autonomous driving, right? So imagine when a car is driving, you have the visual scene is changing, right? So the images just keep coming. And let's say you're in this situation, this is your newest image, and you have this in the history. Now, what we think we can do is use these two images such that we train the network using our technology to better predict this image out of that one. And just train this example. Use this one, predict this one. You make error, correct. Now you you're a better predictor. Now, if you can adjust the network like this, you come to this image, you can now predict better the next one for this particular situation. The network adjusts itself to this particular situation, right? So the idea is that we could have much better performance for autonomous driving with much smaller networks. Now, this would be, okay, that's what I just said. And that's what I just said. But the point is here, now, if suddenly the visual conditions change and you enter a tunnel, then your network would be adjusted to this, would be for a moment confused in a tunnel, but all you need to do is collect 2 images, adjust, and now you're adjusted for tunnel system, right? And now if new visual conditions come that have not been in the training data set whatsoever, the network should be able to adjust itself and perform much better, exactly like human brain does. Right? Another one application that we are working on is speech to text, just by adding the idea of adding new vocabulary for speech to text without forgetting the old vocabulary and without having to retrain with the entire data set, just the new words. Right? So here are some examples. I took some poor speech to text transcriber and used some specific words that were incorrectly transcribed because the system did not learn them. Right? Now, I always get the question, how about large language models? Can we use it? Can one use it there? And the answer is, I don't know. We just started working on one project with language models, not with large language models, but with small language models for simple reason that our resources are small, right? We cannot afford to work on large language models for now, right? And I don't know, but we are exploring it. It's probably multiple good uses of what one can do, but I don't know. Maybe in a few months I will have better answers, right? So, question to you, right? Do you have problems like the following? You have really small amounts of training data where you need quickly retrain. Something happened, really small amount of data, you would quickly need to retrain the network for something. And maybe if you do, talk to me. Maybe we could discover a good use case. Do you have a situation where the world in which the network operates perpetually changes and you seem never be able to collect all the data you need? Right? Talk to me. Does it happen that valuable examples for training are arriving somehow in real time during inference and you would like to somehow get advantage of them? Maybe there is also a use case, right? Final slide. There's a live demo of this technology. If you scan this, it will direct you directly to the live demo. You can play, come up with your own writing system, be trained, test again, writing the same letters, and see how it is doing, how it has learned these letters. Right? You need to take a photo. All right. So thank you very much. That's the same link.
All right. Thanks a lot.